Alright folks, this is my first lecture on gases. To get started, we need to remember our units. We haven't dealt with pressure yet this year. The pressure unit that we typically use is an atmosphere, which is kind of how much pressure you get from the atmosphere. That's at sea level, and you've got to have the conversions to several other units memorized so that you are able to carry out conversions when they're mean to you in problems and they give you millimeters of mercury, which is this guy here, or torr, or pascals, or kilopascals. So the torr and the millimeters of mercury are the same size, pretty much. So 1 atmosphere is 760 millimeters of mercury. And what that comes from is from the mercury manometer, which is a tube full of mercury that, depending on the pressure, the mercury will rise or fall based on how much it's pushing on the pan of mercury that the tube is sitting in. And under typical conditions at sea level, the column of mercury sits at 760 millimeters high. So that's where that comes from, and that's the same as torr. So maybe you'll get units in millimeters of mercury or torr. There's also another pretty standard unit, which is the pascal. You'll see that more on car tires. Could check it out sometime. There are 101,325 pascals in an ATM, and you'll often see that as kilopascals, so that'll be 101.325 kilopascals in ATMs. You need to know those. And you also need to be aware that pretty much everything is using ATMs, all these formulas that we're about to use. So if they give you the other ones, they're being mean and you have to convert to ATMs. What we are talking about is ideal gases. We'll get to real gases at the end of the gas chapter, and what they mean by ideal is, like, if everything in the world were perfect, gases would behave exactly like this. And unfortunately, it's not true. The description of an ideal gas is really close to what actually happens with gases, but it is slightly off. And so when we get to that end, you'll be able to compare the behavior of a real gas, and they mean real, like oxygen, to an ideal gas, which is how the gas would behave if all of our assumptions were entirely true. And we'll get to the assumptions in a minute. There is a law that we're going to get to in a little while called the ideal gas law, which you may be familiar with. It's PV-NRT, PV equals nRT. And R is something that we've encountered last year when we were doing gases. You need to know those values, the value for R as well. It's, pardon me. Typically the value for R, which is the constant in the formula PV-NRT that allows things to work out, the value is 0.08206. And the units are liters times atmospheres divided by moles times kelvins. And those units come from PV-NRT. P is atmospheres, V is liters, there's liters in atmospheres. And then moles is N, and then kelvins is T. So if you are wondering what the unit is and you can't remember, you can just work it out and go, oh yeah, PV over NT, so PV N and T. That's the normal value of R, the one that you're going to use most often. However, in some circumstances, typically when the formula is related to the energy of the system, we've got two formulas like that later on. The value of R is not the same because they're not using atmospheres anymore, they're using pascals, and the pascals work out to give you joules. So if you see something talking about energy, you've got to use 8.3145, or if something is using pascals, but typically it's talking about energy or that kind of thing. So make sure that you know which formulas use which one. Most of them are 0.08206. A couple of them are 8.3145. Now to the assumptions. We were talking about ideal gases, how they make assumptions about the way the gases behave. And this is related to the kinetic molecular theory, which is kind of the thing that describes what the gases are actually doing that causes the behaviors that are observed. So what we can see on a macroscopic level about what the pressure and the volume does, and what the pressure and the temperature does, and what the volume and the amount of substance are doing, that's stuff that we can see. And the kinetic molecular theory is saying the reason that it's doing this is because the gases are bouncing off the walls. They're individual particles. So here are the assumptions. The kinetic molecular theory is assuming that you're dealing with an ideal gas, which is why these two are related. The assumptions: number one, the particles of gas are so small and far apart that you can ignore their volume. So you've got this container or whatever of gas, and 99.9999% of it is empty space. And they're saying basically, let's go ahead and assume that it's 100% empty space, because the particles are so small that they don't contribute significantly to the volume. They call it's negligible. So that's assumption number one, which we will find out is true in some circumstances than others. Assumption two, the particles whiz around and bounce off of the container walls. That's what they do. This is an assumption that we don't really end up canceling out. So you've got your container, and all the particles inside are going. They bounce off of each other as well, and we get into collisions as an important thing when we get to reactions. Assumption number three: the particles do not pull or push on each other at all. That's what they're assuming, which is not entirely true, particularly for some gases more than others, and under certain conditions more than others, because if you've got a gas that's actually polar, there's pulling and there's pushing. And so assumption number three is true to a greater or lesser extent, and you'll have to be able to explain why. And then assumption number four, the kinetic energy of the particles is directly proportional to the Kelvin temperature. The kinetic energy is 1/2 mv squared, the mass times the velocity squared, and we'll get into that later again. But when you're asking how much energy does this particle have, what's important is basically what temperature is it? What's the temperature of the entire sample? And so, but you've got to use kelvins because that's your absolute temperature. Celsius doesn't work. So typically you're not able to use Celsius when you're doing these formulas, and you have to remember how to convert from Celsius to Kelvin, which is to add 273 degrees. So 4 assumptions, 2 of them are yes, definitely, and numbers 1 and 3 are, well, it depends on your situation, and you need to be able to explain that. We'll do more about that later. All right. So I was talking about how the kinetic molecular theory explains some observed behaviors of gases. And the first one that anybody really noticed was that the pressure and the volume of a gas are inversely proportional. And this was observed first by Robert Boyle. And he had some gas that was trapped behind some mercury, and he would add more mercury, and then the gas would get squishier and take up less volume. And he's like, whoa, if you squish it, it gets smaller. That seems sort of obvious to us, but it didn't back then, because they didn't understand gases at all. They didn't know that they were made of atoms. Atoms and molecules. This actually helped contribute to the understanding of particles and atoms and molecules and stuff. So he observed that, hey, if I increase the pressure, then the volume of the gas goes down. That's inverse, 1 up, 1 down, and that means that it's a multiplying formula. And the kinetic molecular kind of reasoning behind this is that if you make the volume of, if you decrease the volume, the particles are closer together. And when they're closer together, they'll hit the walls more frequently, so you've got more pressure. So that's the explanation for that observed behavior. When you're dealing with this mathematically, typically the formula that you're used to is P1V1 equals P2V2. And that's gives you the ability to compare when a system starts off in one state and changes to a different state. But initially it was P1V1 equals some constant. He was saying that, you know, every time I do this experiment, if I hold the temperature constant, the pressure times the volume is the same number. So it's really kind of P1V1 equals a constant, which equals P2V2. So be aware of that. And also you can derive this from the ideal gas law, PIVNRT, PV equals nRT. If you consider that N, the number of moles, is going to be the same when you're dealing with a system that's changing, that's only changing its volume or pressure. So N ends up canceling out. Temperature ends up canceling out because you're holding temperature constant. And so you end up with P and V being the only things that change. They're the only ones left. You gotta remember that pressure is only in atmospheres when you're using it with the ideal gas law, because your R, your constant R, has to have atmospheres in it if you use the 0.08206 value. When you're using the two systems, pressure 1 and pressure 2, you can actually get away with using millimeters of mercury or torr or pascals because the units cancel. So when you're using P1V1 equals P2V2, you don't have to be picky about using ATMs. But when you're using PV equals nRT, you do, because your R requires ATMs. This is Boyle's law. It's named after the dude that observed that pressure and volume are inversely proportional, and that also they multiply together to be a constant. All right, so that was the first thing that we saw with gases. And the second thing that was seen with gases was that pressure and temperature are directly proportional. So if you increase the temperature, the pressure will go up. This was observed by Jacques Charles, so it should really be Charles's law, but they say Charles, oh well. And the reasoning behind that, the kinetic molecular theory for why that happens, is, you know, you've got this container, it's full of gas, it's got particles, they're bouncing around. When you make it hot, the kinetic energy of the particles goes up because of the kinetic energy being directly proportional to the temperature. Kinetic energy is 1/2 mv squared. So you're increasing the kinetic energy, either the mass of the particles or the velocity of the particles is going to go up. You can't really increase the mass. So they go faster. When they go faster, they hit the walls more, and pressure is basically how much force is being applied to the walls. So if they hit more frequently, then you've got more pressure. And mathematically speaking, you've got PV equals nRT. Your R is still that constant that requires the ATM, and the T requires Kelvin because it's absolute. And when you're comparing a system that you've changed from one state to another, it's a single system, so the number of moles stays the same. The volume is staying the same because you're holding volume constant in order to observe this. So N and R and V all cancel out, so all you've got left is T, and so you move T over, that's P1 over T1. And also what Charles actually observed is that pressure over temperature for a single system is constant. So again, this is really P1 over T1 equals a constant equals P2 over T2. And because we're comparing two systems, the same system under two different conditions, you can get away with cheating on the units for P. So you can use millimeters of mercury here. However, because of assumption 4, it's directly proportional to Kelvin temperature. You've got to use kelvins for the T's. This is Charles' law. All right, number 3. This one is kind of a combination of Gay-Lussac and Avogadro. And what they figured out was that if you've got your pressure and your temperature constant, you have a certain volume of gas, that's a certain number of particles of gas. And we actually know this as one of our equalities, that at STP, which is standard temperature and pressure, when you're holding pressure and temperature constant, your volume of 1 mole is 22.4 liters. So this is something that they observed. And the reason for this is if you've got more particles, you've got more particles hitting the walls. So more particles, more pressure, and the volume is basically determined by how many particles there are. It doesn't matter the size of the particles, because if you remember, the particles are so small, assumption number 1, that you ignore their volume. So this works for helium, and it works for uranium's hexafluoride, this enormous freaking molecule. So it... I lost my train of thought. So that's that. Mathematically speaking, you've got PV equals nRT. Again, R is the constant. And since you're holding pressure constant, and R is a constant, and you're holding temperature constant, all you've got left is V and N. So that's V1 over N1 is equal to a constant, which is equal to V2 over N2. Volume is usually in liters, but you can use milliliters or gallons or whatever here, because again, when you're comparing the same system twice, those units will cancel. And N is the number of moles. It doesn't really come as anything else except sometimes they'll be mean to you and give you the grams, and assume that you would notice that you had to convert into moles, because that's what N is. This is Avogadro's law. This one isn't as common to run across as Boyle's law and Charles's law, but it's important because it's the third piece that allows us to construct the ideal gas law, because we've got the relationship between pressure and volume, pressure and temperature, and now we've got volume and number of particles. All that's left is R, which is a constant, so we can just work it out. So oh, and don't forget that standard temperature and pressure is 1 atmosphere and 0 degrees Celsius, which, why isn't it in Kelvin? I don't know, 0 is easy to remember, which is 273 Kelvin. All right, now for problems. Go ahead and pause and go and do problems, 1 through 5, on the back here, and we will come back and I will show you my answers. Okay, here we go. Question 1, convert 583 millimeters of mercury to ATMs. That's going to be like this, using your dimensional analysis. 583 millimeters of mercury times, bring your unit down and put the unit you want on top, and remember the equality, which is that 1 atmosphere is equal to 760 millimeters of mercury, which works out to be 0.767 ATMs. All right, number 2. No, not number 2. Part B, let's say. Then you've got 3 atmospheres, converting to torr, which is 1 atmosphere is equal to 760 torr. Why do they have 2 that are the same? I don't know. Deal with it. It'll be okay. 2280 torr. Bam. All right, this one. 500,000 pascals to ATMs. That's 500,000 pascals. Bring down your unit pascals. put up your unit ATMs. 1 ATM, you must remember, is 101.325 pascals, and that gives you, considering sig figs, 5 atmospheres, because there's only one significant figure here in the 5. But my calculator says 4.93, neener. Alright, 2,000 kilopascals. That's 101.325. That's a tiny point. And 1 ATM is equal to 2 atmospheres, again with the single sig fig here. Alright, question 2. A diver at a depth of 100 feet, where the pressure is 3 atmospheres, exhales a small bubble of air with a volume equal to 100 mils. What will be the volume of the bubble at the surface? What we have here is a single system under 2 sets of conditions. We have a higher pressure and a lower pressure and a volume that is changing. So what we have, and also be aware that the 100 feet is a sneaky number that you don't need to know. That happens sometimes. Alright, pressure 1 is 3 atmospheres. Volume 1 is 100 milliliters. What will the volume be at the surface? There's only 2 numbers. It's true, but at the surface of presumably the ocean, should have said that, is 1 atmosphere. So pressure 2 is 1 atmosphere at 0 at sea level there. And volume 2 we don't know. So P1 V1 equals P2 V2 is your formula. And so that's going to be 3 times 100 equals 1 times x. And that gives you x equals 300 milliliters. Bam. Alright. The volume of a gas held at constant pressure is to be used as a thermometer. If the volume at 0 Celsius is 75 centimeters cubed, what is the temperature when the measured volume is 56.7 centimeters cubed? You need to remember that a centimeter cubed is the same thing as a milliliter. Otherwise, that unit might freak you out. So, as a thermometer, that means that the volume will be changing as the temperature is changing, and you could look at it, for example, and be like, whoa, dude, it's bigger, it's hot. So what we have is the volume 1 is 75.0 centimeters cubed. The temperature 1 is in Celsius, but it needs to be in Kelvin. So 0 degrees Celsius is 273 Kelvin. Volume 2 is 56.7 centimeters cubed, and T2 we don't know. So that's V1 over T1 equals V2 over T2, which is 75 over 273 equals 56.7 over T2. And solve for T2, which gives you 206 Kelvin. Bam. Alright, 4. A 16.6 liter sample of gas contains 9.2 moles of fluorine, which is diatomic. How many moles of gas would there be in a 750 milliliter sample at the same temperature and pressure? What we have is volume 1, 16.6 liters. And moles, that's N, so that's N1 is 9.2 moles. And the question is, in how many moles would there be, that's N2, we don't know, at this volume, which is 750 mils. Now, notice, they were meanies. The units are not the same. 750 milliliters is 0.750 liters. Don't let them trick you. Who's them? It's kind of me. Alright, and the formula for this is V over N, 1 equals V2 over N2. And let me just show you the derivation of that from PivNert. What we have is V and N. So let's rearrange so that we have V and N. on one side and everybody else by themselves on the other side. So that's going to be V over N equals RT over P. So we rearranged the formula so that V over N is RT over P. And what you need to realize is that we're holding the temperature and the pressure constant, and R is a constant. So this ends up being the same for V1 and N1 as V2 and N2, because these guys are all the same number for both situations. And that's why you can say V1 over N1 equals V2 over N2 and ignore this part here. So that gives us 16.6 over 9.2 equals 0.750 over N2, and N2 ends up being 0.42 moles of gas. And question 5 says, discuss figure 10.9 on page 400 in your Brown textbook. What does it show? What does it imply? I have found basically the same graph here on the internets. And what this is showing is we've got your x-axis, which is temperature in Celsius, and your y-axis, which is volume in liters. And you've got your data points, which are all these triangles that someone has put in. And what it shows is that, number one, there's a nice line, which is the relationship between volume and temperature. When temperature goes up, volume goes up. So that's a direct relationship, and direct relationships have graphs that go up like this. Inverse relationships have graphs that go down. So here we have the direct relationship between volume in liters and temperature. And here are all the data points of somebody who did a lab or whatever and measured the volume of the gas at all these different temperatures. And apparently they have a fancy lab because they were able to get their gas all the way down to a negative 196 degrees Celsius, which is cold. And I don't think that our freezer would do that. And they found that this mole of gas was something like 7 liters. And there the data has to stop because at this point the gas actually condenses to a liquid at 1 atmosphere, and so you aren't able to continue the experiment all the way down. But what's interesting is if you had a gas that was ideal, it wouldn't have any attractions that would allow it to condense. So an ideal gas, you would be able to get data points going farther down that would continue this really pretty line. And that's what this dashed line is somebody saying, well, if we were able to keep on going, if the assumptions about ideal gases were actually true, then when we get down to a certain temperature, we cross this x-axis here. And what's interesting is that the x-axis there is 0 volume. There is absolutely no volume to the gas at a particular temperature, and that temperature is negative 273.15 degrees Celsius, so 0 degrees Kelvin. That's absolute zero. You can't get colder than nothing, and that's why it's called absolute zero. And we haven't actually gotten there because we're not dealing with ideal gases. They do have a really small amount of volume. We've gotten within a single fraction of a degree, very small, but we haven't quite gotten there yet, and I don't think we're going to, because there are no ideal gases. They're all real. Whee! And I'm not going to write that down. I'm just going to talk about it, which means that we are done. Bye.